Another property of elements that we want to discuss and their trend on the periodic table is something called ionization energy. What is ionization energy? Well, the definition is the energy needed to remove an electron from an atom. And if we want to break down this word to understand why is it called the ionization energy, remember, an ion is an atom with a charge that's not neutral, so either positive or negative. So essentially what this is saying is if we remove an electron, we know that's going to alter the charge on the atom. So this is the amount of energy needed to make an atom into an ion. So let's talk about an example. Let's say we have sodium here. Why would an atom want to lose an electron? Well, sodium is a group 1 metal. It has one valence electron. This is a Bohr model, which is our older representation of atoms. But we know that in order for this atom to satisfy the octet rule, in order to have a full valence shell, it wants to get rid of this electron, remove it. Because then this third energy level will no longer have any electrons in it, and it will now have a full satisfied valence shell. So if we express that as an equation, what we would say is, for sodium, Na, let's say it's in the gaseous form, to turn that into Na plus, that must have meant that we lost one electron. So this would be an equation for the ionization of sodium. The amount of energy needed to do this, the energy needed, that would be called the first ionization energy, because it's the amount of energy needed to remove the first electron from this atom. Well, let's break it down. Why would it even need to take energy to do this? Well, we know that electrons are negatively charged, and the nucleus is positively charged. So there's this attraction between the nucleus and the valence electron. So it's going to take some energy. We're going to need to add some effort, some energy to rip this electron away from this positively charged nucleus. Let's say we now have the ion Na+. We know that this atom still has, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons still. So let's say we wanted to turn it into Na2+ by removing another electron. We totally could. But since this is now the second electron that's being removed, the energy needed would be called the second ionization energy. And we could go on and on depending on however many electrons we wanted to remove. We can look at the first, the second, the third, the fourth, the fifth ionization energies for a variety of atoms. But what we really want to get out of today is to be able to understand what is the trend on the periodic table, how does ionization energies change for different elements based on their location, and why does that trend exist? Well, what we need to know is if we look at the periodic table, as you go up a group, and as you go across a period from left to right, ionization energy, which I'm going to abbreviate as IE, increases. In addition, it's the same going up a group. Ionization energy increases as you go up a group. Okay? Therefore, the element with the greatest ionization energy, and here we're talking about first ionization energy only, would be helium. It takes more energy to remove an electron from an atom of helium than from an atom of hydrogen. Or if we wanted to compare, sodium and potassium, to remove the first electron, it takes more ionization, it takes more energy to remove the first electron from sodium than from potassium. What we really want to understand is why. Why is this trend the case? Well, let's first break it down for periods. So from going right to left. Why, when we go this direction, does the amount of energy needed to remove the first electron increase? Well, if we think back to what we know about atomic radius, we know that as we go to the right on the periodic table, the atomic radius decreases. And for a quick refresher, that's because the effective nuclear charge is greater over here than over here. So if we were to draw these, let's just say we drew a Bohr model of boron. Okay, it has 5 electrons, 1, 2, 3, 4, 5. And if we drew fluorine, we know since it has a smaller atomic radius, it would look, something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. This distance right here, we'll call it R. And this distance, we'll call it R2. R1 is less than R2, which means this valence electron is closer to the nucleus. It's closer to the positive charge. So essentially here, this electron is getting pulled more towards the nucleus. Or what we could just say is that the attraction between the nucleus and the valence electron is a lot much larger. Since there's a stronger attraction, that means it's going to need to take us more energy to rip one of these electrons off. Since over here, another way of saying that conversely, is that since this electron is further from the nucleus, there's less attraction between the proton and the electron, so it's going to take less energy to remove that valence electron. So that's the explanation as we go to the right. What about going down a group? Well, we know as we go up a group, the ionization energy increases. And guess what? It's actually for the exact same reason. Beryllium, 4 electrons. We'd put those into 2 energy levels. We'd look something like this. These are our group 2 metals. And if I drew magnesium, it has 12 electrons. That's going to occupy 3 energy levels. So these are a little bit messy Bohr models, but you'll get the idea. But we can see here, it's the same idea. This atomic radius, R2, it's much greater than R1. So if we wanted to remove a valence electron, let's say this electron here, this electron here, which one would be easier to remove? Well, it would be from an atom of magnesium. Because this electron is further from the nucleus, so there's less attraction between the nucleus and the valence electron, so it's going to take us less energy to remove it. Conversely, as we go up, the atomic radius decreases, meaning there's more attraction between the valence electron and the nucleus, so it's going to take more energy to remove it. So that's the explanation for the trends of ionization energy. Think atomic radius, think effective nuclear charge. These are the vocabulary words that we need to be using when we're making these explanations. But what I want to do next is connect this to electron configurations. So for example, let's say we had sodium from before. Okay? First, we want to make sure we can write the electron configuration for sodium. So sodium has 11 electrons. We know we're going to fill up the first energy level, the s orbital, with 2 electrons. Then the second energy level, s orbital with 2. Second energy level, p orbitals with 6. Then we're going to go to the third s orbital, and we're going to put 1 electron in there. If we were to draw this on an energy diagram, just for refresher, 1 s orbital is lowest in energy, then the 2s, then the 2p, which is consisted of our 3 orbitals, the px, the py, and the pz, and then the 3s. So if we filled these up with 11 electrons, 2 go in the first, 1, 2, 2 go into the second energy level, s, 1, 3, 4, and 6, 5, 6, 7. Remember, each orbital needs to be occupied by 1 electron before we can start doubling up. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now my p orbitals are filled, so I have to go to the next available energy level, which is a 3s, and there's my 11th electron. So when we say that we want to ionize Na, we want to turn it into Na+, that means we're going to remove an electron. Well, which electron are we going to remove? We're going to remove the electron that's furthest away from the nucleus, the one where that requires the least amount of energy. And we know that this 3s, we're in the third energy level. This electron is going to be the one that's furthest away from the nucleus. We know that for a couple reasons. Number one, it's in the third energy level. No other electrons are in the third energy level. And we also know that it's further away from the nucleus, which means there's less attraction, so it's going to be easiest to remove. So if this electron gets removed, we can see that what we would have left, if we drew the potential energy diagram again now, would be 1s, we'd have 1, 2 electrons, 2s, 1, 2, 2p, 5, 6, 7, 8, 9, 10. We no longer have an electron in that third energy level in the s orbital. So the new electron configuration would be 1s2, 2s2, 2p6. What we want to be able to know how to do is explain first the definition for ionization energy, understand that there can be second ionization energies and third, depending on how many electrons we're removing. We know the trend that as you move up a group and to the right on a period, the ionization energy increases, the first ionization energy. This is true as we go across periods because atomic radii decrease as you move to the right, which means there's more attraction between the nucleus and the valence electron, a greater effective nuclear charge. Same explanation for going up and down groups. And then we need to know how to write electron configurations for atoms depending on if they're ionized, as they are here, versus if they're not ionized here. An extension question would be to think about, well, this is the first ionization. What about for the second? Which electron would get removed next? Well, all of these electrons here, 1, 2, 3, 4, 5, 6, are on equivalent energies. The px, py, and pz orbitals are at the same energy. So really, we don't know which one of these we would remove. It could be any one of these 6 electrons in the 2p orbitals. But if we could, we would have Na2+. What would the new electron configuration be? Well, maybe 1s2, 2s2, and now 2p5. Because one of those electrons would be removed. We're going to get a lot of practice in class looking at data and analyzing this, but these are the trends you need to know.